Okay, so we're going to continue here. I've been working away at implementing more of the parser, and I was working on this next grammar rule, postfix expressions. And so examples of these would be the array index expression, so like my array bracket 7 close bracket. These two I have not gotten to yet, but they are function call syntax, so you could have you could be passing no parameters or an argument list, no arguments, I guess. This grammar rule is for the postfix expression for field accessing a struct object or a union object with the dot. This is the arrow operator, so if you have a pointer over here, you do arrow and then an identifier, and it's the same as dot access. And then these are increment and decrement, so this is the plus plus operator and the minus minus operator. I'm not actually planning on implementing the decrement operator until I absolutely have to. None of the code in the compiler uses it. However, it does. I am using the increment operator, so I'm going to parse that. Okay, so I was working along. This is what I have. So a postfix expression could be a primary expression. So the first thing we do is we try to parse a primary expression, and if we get it, we return. All right, and there's a bug here. We'll see in just a bit. But this is sort of the naive approach that I took. Next, we need to parse. Okay, so if that does not work, we need to parse the postfix expression. So that is a recursive call to the function we're defining. And then, so we save all of these begin with postfix expression. So we parse one. If we can't, we return null because we failed, and we store it in this variable child. Next, we're going to check for like this character, this token, this token. So for array index expressions, we do Left-recursive on the open bracket. For dotted field access, we would use token dot, token arrow for the pointer access, and plus plus for the plus plus operator, postfix operator. And at the end, if none of that works, we return null. So then inside of each of these expressions, or inside of each of these if blocks, we sort of do the obvious thing. We need to parse the index expression, so that would be this internal expression for inside of an array index expression. And then we expect a closing bracket, and then finally we malloc some memory and set the tag and assign child, which is this first parse postfix expression, to a member called array, and index is this sub expression that's inside of the brackets, and that goes in there too. And then we return the expression. So it's very similar with all the other ones too. Just sort of busy work that I have been working on. So I was like, okay, I should probably test this, and I'm glad I did. So I decided to do a test where we just test like all three of these, or I guess not all of them, but almost all of them all at the same time. And I suppose I could put like 100. That way we test all of them at the exact same time. Oh, and one last thing I should mention is in parse expression. Previously this had been parse a primary expression in here, but now our most advanced expression parser is the postfix expression. So when we want to parse just a general expression, we should be parsing the most powerful, using the most powerful parser. So I had to make that change. Okay, so we're down here, and let's try to parse this. I will run this example We'll run our tests, and okay, so we should see false printed out, and then hopefully this expression. We're just displaying the expression, so we see false here, and then right after that we see my dog. Hopefully you can see my cursor here. I'm trying to highlight what I'm pointing at. We see my dog, which is the first part of this source text, but we don't see anything else. So we only like chomp the first part of this, and you may have already figured out why that is. It took me a little bit to figure out. If I go back up to our parser for postfix expressions, a primary expression could be an identifier. And if we parse an identifier, if we get an identifier first, or actually any primary expression, we're going to immediately break out of this entire function and not parse the rest of the stuff that could be there. And this is a problem because obviously we do need to parse the rest of it. And I believe, so I was thinking about like how to solve this problem. And I believe the problem comes down to the fact that this grammar does have some left recursion. So left recursion is when the non-terminal that we're defining has itself as its first component in the sentential form here. So in order to parse a postfix expression, first you need to parse a postfix expression in at least one of these cases, and it turns out in most of these cases that's how it is. And so, you know, what one thing you might try to do is we could try moving this code all the way to the bottom, and I think I tried this. Let's try it again and see what happens. So we could say, oh, well, let's just reorder it. So effectively, let's move this all the way down here, and we'll parse a primary expression last. The problem with that is, in order to, now we have direct, in the C code itself, we have unbounded recursion. So if we just say, okay, call parse postfix expression, well, we do a little bit of setup here, but then the first operation we actually do is call parse postfix expression. And that's a problem, because then we're just in infinite recursion. We're going to blow out the stack and not get any work done. So that doesn't work. That is not a solution. I'd like to take a detour into a little bit of grammar manipulation to sort of try to solve this problem. We will figure out how to solve this problem. So I'm going to copy this. Oh, I should move this back up. And we're going to copy this into a separate buffer. Just a temporary file. Temp.txt. Can I do like ebnf? Search the marketplace for ebnf. Is this just highlighting? Yeah. No, actually this is yak, right? Extension yak. Yeah, okay, this is what we want. So this is a yak grammar file. So let's close this, and then I want to rename this quickly to yak. Okay. And paste this in. Nice. Now we have syntax highlighting. Okay, whatever. Okay, so we need to get rid of the left recursion. And the way I'm going to do this is we're going to do some transformations on this grammar. this is just exploratory at this point. I'm not really going to change the grammar. But let's simplify it first. Let's just keep these two rules in the grammar. And let me make this bigger. I'm going to close that. I'll make this nice and big. All right. So there are only two rules in this entire grammar now. A postfix expression could be a primary expression, or a postfix expression followed by these two. Actually, you know what? I'm going to change this to the other rule that we had, which was identifier. Okay, so these are the only two rules. So if we think about what this, hang on. First, what I'd like to do is change this to be, I'd like to make this a little bit easier to read. So I'm going to call this, instead of postfix expression, I'm going to call it F for postfix. And then for primary, I'm going to call that M. Postfix is F. And then identifier, I'm going to call ID. Okay. And this is a terminal, so maybe we'll do lowercase. I don't know. Or maybe these should be lowercase. And you know what? We're going to use the regular syntax for the sort of the math notation for grammars, because I think that'll make it more clear. Okay, so this is our rule. We have a postfix expression and we have a primary expression, and then we have these two terminals, dot and ID. Okay, so if we think about what this actually generates, the language that this generates, well, an F could be reduced to an M, and then we could be done, right? So that's one case. Or we could have an F could be reduced to an F, a dot, and an ID. F dot ID. Okay, but then F is still a non-terminal, so we need to reduce that again, and we find, oh, well, this could be M dot ID. Okay, and now let's assume that M is sort of a terminal. In this case, we know that it's not, but I'm not going to expand out M. So we've got M, or we could have M dot ID. Another thing that F could be expanded to is F dot ID again, but then instead of the F being transformed into an M directly, we could transform the F into F dot ID, right? So I'm putting these parentheses in here just for our clarity, and then at this point maybe the F gets transformed into an M. So now we've got M dot ID dot ID. So I think we can see the pattern here. We could either have a primary expression, or we could have a primary expression followed by dot ID, dot ID, dot ID, dot ID, etc. So any number of dot IDs. If we were thinking about this in terms of regular expressions, maybe you could express this like this. So 0 or more occurrences of dot ID following the M. There's a standard way to transform a grammar from one that involves left recursion like this. This is where the left recursion comes from, but it doesn't. I think I'd rather take a different approach here, because that would, in order to do it sort of the mathy way, you would add like an F prime, and I don't really want to do that. I don't want to add extra rules. So we're just going to parse effectively this regular expression. I mean, it's not really a regular expression, but all we have to do is we have to say, okay, so in order to parse an F, first you need to parse an M, And then you need to parse 0 or more .ids. Okay. And when we are doing this parsing in C, when we're actually writing the parser, we will need to make sure that we structure the AST in such a way that it makes sense. So for instance, if I have my dog dot birth date dot year dot first number, I don't know, just an example of like a long dotted identifier string. This ought to be parsed as first we do my year dot birth date, next we do that thing, we apply the dot year on there, and finally we do dot first number. So we need to parse it in this way. If we had done it in the opposite direction, that would actually be incorrect. So let me think about what that would look like. If we had done something more along the lines of this, yeah, I think that's the opposite. Yeah, clearly that's wrong. Clearly we're not looking at like the year struct, getting the first number, and then that gives us like what, a string that we look up in the birthday. Like this just doesn't make any sense. So we just need to be mindful that as we're doing effectively a fold on this sequence of identifiers, that we construct the AST in the right direction. Okay. So now let's bring back our full grammar. Let's bring this back over here, and let's think about this again. So postfix expressions. So essentially we're transforming this into primary expression followed by 0 or more. So I'm going to do star at the end of this. 0 or more of these. We could have this, or we could have, maybe I should do this like this, or we could have this, or we could have this, or, so we actually, instead of the .id, which is what we were thinking we would have to parse, we actually have a whole bunch of variants in here that we need to make sure that we're keeping track of. So .identifier, or PTR op, which is really that token identifier, or the plus plus operator. Okay. So this is actually what we need to parse, and these are the only ones that I'm focusing on right now, just these 4. So this is essentially sort of like the regular expression that we're going to parse. It's really not a regular expression, but we're going to think about it like that. So now let's go back over to our parser. And I think I'd like to rename this from expression to maybe we'll leave it like this. So the first thing we need to do is we need to parse a primary expression. All of these begin with a primary expression. So this part is correct, parse a primary expression. This part is incorrect though. So I think what we should do is say, okay, if you can't parse a primary expression, then we need to return null. Like, that's a problem. But assuming we can, the next step is we're going to do essentially a while loop. So this this star in regular expressions means 0 or more occurrences. So it's not going to be a do while, it's going to be a while loop. And I think I'd like to just use while true, and then we'll break out based on other conditions. Let's think about this. So parse postfix expression. I think we do not need this anymore. And I'm going to move this brace down to the bottom. And I think I'd like to keep this return null at the bottom of the loop, but we'll see. That's probably going to have to change, but we'll get there. Okay, so in fact, maybe we should comment out everything except for the dotted field access, which was our example. Let's comment out everything else inside this loop and just focus on this. Okay, so if we can accept the dot token, then we need to expect an identifier token, and the Lexer arrow token value is the name of the identifier, and that's the field name. So this makes sense. So we're storing it in expr. I believe what we'd like to do is actually make a new variable here. So instead of expr, I'm going to say struct expr pointer field expr. Let's just keep it simple. And then here we want field expr, field expr, field expr. Child is the name of something we had previously, but I think at this point we actually want expr to be the object. So the first thing that we parsed was the primary expression, and we stored that in expr. We might need to rename this eventually. I'm not sure what a good name for this would be. Okay. So size of field expr. Okay. The tag is expr.fieldAccess, and the field x we will say field expr as field access. The object is going to be the previously parsed thing. Okay. Now we set the token. The token is, or we set the field name, which is token, which is effectively the identifier. And then we're not going to return. So this is where things change. I believe what we need to do is we need to say expr is equal to field expr. And then continue. So continue the loop. We go back to the top. So on our next pass through the loop, if we can parse another dot, then we need to expect another token, and we'll do this again using the previously set value for expr, and we keep building up this chain, this like deeper and deeper nested object, and continue to continue. And I suppose that means if we do not get a dot here, then we should return expr, like exit the entire function, returning expr. And so that should be definitely at the bottom of the loop. And that sort of answers our question as to should we be returning null. Maybe what we should do is put this all the way at the bottom in case, Well, this is a loop forever. And we'll say break at the bottom. This is a weird loop. I was just sort of concerned that maybe if this entire thing gets skipped, but it can't be skipped because it's while true. Okay, so assuming we only parse a primary expression, you know, this will return true. We'll continue through here. While true, that's obviously we're going to enter into here. This will be false because there's not a dot here. We'll get to the bottom of the loop and break out of it and return the expression. So that's the primary expression that gets returned. Okay. I don't know, that feels kind of weird. And then we're saying continue here. Okay. All right, I guess this makes sense. Let's test this out before I go and do this to the entire thing. We'll take our test here and put this I will comment this out temporarily, delete that, and paste this in here. Oops, undo. Okay, so we should see this entire string get, or this entire thing get printed out. Let's try it out. Yes, okay, that worked. Yeah, so I've been updating the printing functions as well. Okay, so that works, which tells me that we should be able to go back up and use this sort of as a template. Use this as sort of a template for the other cases. So array index expression. Let's uncomment this. And we will say, yes, we need to accept an open bracket. We need an index expression, so that's here, and then we expect a closing bracket. And then here we need a new struct expr pointer, and we'll call this array index expression. Or maybe we should just be calling this new expr. New expr. Maybe that's a better naming convention here. Instead of child, we'll call this, we will set the array, which is the first part, this expression, will be the currently parsed, or the most recently parsed expression. So that is, that's what we're calling array, because it has to be an array, or a pointer, I suppose. And then instead of return, we do expr equals new expr and continue. Okay. I'd like to change this to new expression. New expr. New expr, and this becomes new expr. Okay. Let's do arrow field access. We expect this is going to be almost identical to dot field access. In fact, I think I can literally just copy all of this over, and then let's just check because the only difference is okay, so one difference is we parse a dot, and here we parse an arrow. The only other difference is this tag is going to be expr arrow field access, and field access is the same object, struct name, so, or union variant or whatever. Okay, and then finally we have the postfix plus, and here we want struct expr pointer new expression. We're going to malloc. Oh, that's right. I should be saying new expr here as well. Okay. Oh, and field expr is no longer real, so new expr. All right, that would have been caught by the compiler, thankfully, but new expr. Okay. And we will say new expr here and here. And instead of child, it's the currently built up expression. And then finally here, we're going to say we succeeded in parsing a ++ expression, so set the expression to be new expr. The most recent expression parsed is new expr. And finally, we say continue from the top of the loop. Okay. So let's test this out. If we go down to our test, we should see this printed out. Yes. All right, that's great news. Okay. Let me see how long I have been streaming. 32 minutes. I think that's a good stopping point for here. What we've talked about, to recap, is how to deal with left recursive grammars when using a limited parser. And I back and look at the Wikipedia article. That's very similar to what they're doing here. So where is an example of left recursion in their grammar? Condition, expression, factor, a term is a factor. Maybe they don't have left recursion in here. Okay, so yeah, often what you'll do is you will sort of add new non-terminals like expression, term, and factor. You'll transform your grammar so that it does not have left recursion in it by adding new non-terminals that sort of break things down. In our case, if we wanted to do that here, I can quickly show how that transformation works. This is something I always have to sort of rederive for myself. But since we're trying to parse m followed by 0 or more .ids, we can just sort of think about this, and we can say, okay, well, let's say that f parses to m followed by f prime. Okay. Or f produces just m. Okay, and f prime will sort of be the tail. F prime will represent... Oh, it does not like... Okay, the syntax highlighting doesn't like this, but whatever. F prime will sort of represent this this tail of .ids. However, we don't need 0 or more. We actually need, because the 0 case is handled here. So we will say f prime goes to dot followed by id. D followed by F prime. So what's interesting here in this transformation is we had left recursion here. F goes to F followed by some other stuff. And we've sort of transformed that into almost right recursion, I guess you could call it, where it's F prime and there's the F prime on the end. But since we're parsing from left to right, that's not a problem anymore. So I'm not even sure if right recursion is a name for this type of grammar, but it's certainly not a problem for our parser. So I think this might also have worked. This alternate grammar, I think that might have worked in our case, but I would rather do it in this way. That makes